Hi, I'm Mark Stephenson from the Autonomous Vehicle Systems Lab at the University of Colorado Boulder, and today I'm going to be presenting on reinforcement learning for Earth-observing satellite autonomy with event-based task intervals. So first, we're going to talk about the Agile Earth-observing satellite scheduling problem and how we're going to formalize it for use with reinforcement learning. So the Agile Earth-observing satellite scheduling problem. We know what a satellite is. In this case, we're typically looking at a low Earth orbit satellite. Earth observing just means that it has some instrument to gather data about ground targets. These targets are heterogeneous in reward and distributed across the surface of the Earth. And they might be subject to some sort of constraints about when they can be imaged, such as an elevation constraint or a time of day constraint. The agile aspect of this means the satellite can both image targets across track and along track. So this really means that the satellite can choose when to image a target across a window of time. Finally, the scheduling problem aspect of this is simply the fact that we want to maximize the sum of rewards for the targets that we image. So there are really two approaches to this problem, these pre-planning based approaches and reinforcement learning. So these pre-planning approaches like mixed integer programming or iterative local searches tend to be good because they can have pseudo-optimality guarantees, and they're also scale well to allocation problems between mini satellites. However, they do have some drawbacks. They are slow for large problems. They can take hundreds to thousands of seconds to find a solution. They are only as good as whatever abstract model is being used to represent the search space for the solution, which means that for certain system dynamics that are nonlinear or otherwise complex, it can be difficult to properly model those constraints on the problem. Finally, this is an offline method. These are expensive plans to generate, to upload to the satellite, and because of the computational cost to generate them and the time to generate them, you can't really fix them in the loop. It is possible to do some small repairs on board to the plan, but by and large, you're stuck with the plan that you originally generated. So for reinforcement learning, there are a variety of pros that kind of overcome these cons of the pre-planning approaches. It can be very fast to evaluate on the fly on board the satellite. It can learn about any effects that you can simulate, not just whatever you can model within some constraints of your optimization framework. And it's an online solution method. It will pick the best action with respect to the current state, which means that it's going to be responsive if your requests change or you have some unexpected event happen to the satellite that might prevent you from completing your original plan. It's possible to implement safety guarantees, which we'll talk about some later. And we even see some cases where reinforcement learning generates policies that are perhaps smarter than what a human would come up with. For fairness, of course, we need to talk about the cons of these methods as well. You lose the optimality guarantees, and the training costs for these policies can be expensive on the order of tens of hours. So to formulate the Earth-observing satellite scheduling problem as a Markov decision process, we need to define a few aspects of the problem. We start with our observation space, which is a deterministic subset of our simulator state. This includes things like the dynamics of the satellite, so where it is, where it's pointing, how it's moving. And then we also include information about the next M targets, so where they are, what their priority is, so how valuable are they to us. The action space consists of actions for the next net N targets with upcoming requests. We have an action corresponding to attempting to image each of those. Of course, it isn't necessarily possible to image some targets. Their opportunity window may close before you have time to slew to and settle on those targets. The reward function is very simple. We get the reward equal to the target's value if we fulfill the request. Otherwise, we don't get any reward. So one of the innovations of this work is using event-based intervals. And this really comes about in how we define our transition function. So how does our system evolve from one state to the next? This is ultimately a deterministic process from an underlying simulator. And in many cases, it'll consist of just moving the simulation forward by one step. So you might think of one control cycle if you're doing some low-level control problem, one turn in a game, or one duration of a action. In this case, though, fixed duration steps will lead to downtime when actions are completed. So if we slew to a target and we image it, that we allocated 3 minutes to image this target, suddenly we have downtime once the target's been imaged. And we know that our optimal solutions aren't going to waste time like this. So what we do is we use event-based intervals. We propagate the simulation at each step until one of 3 different conditions is met. The first is that we've successfully imaged a target, because if we have, our request is fulfilled, there's nothing more we can do with it, let's go pick a new action. The second alternative is if imaging is unsuccessful. Once the opportunity window for request closes, you aren't going to be able to get any value from continuing to try and image a target that's unavailable, so you might as well pick a new action. Then finally, to prevent certain sorts of bad behavior, we just limit any of these steps up to 5 minutes, and that just keeps us from getting stuck on a target that we've picked halfway around the world, which can really help with both training and the deployment of shields later on. So before we go deeper into the training process, here's an animation of what this looks like in practice. We have our satellite going around the world. The dots all correspond to targets, which are roughly the locations of cities. Red open circles are the targets that the satellite is choosing between. And then once the target is selected, we get that line between the satellite and the target. And finally, if the satellite successfully images a target, the request is marked as fulfilled and turns red. So to train this agent, we want to train over a variety of scenarios. We randomize the orbital parameters of the satellite within the set of 45-degree inclination orbits. We also look at different distribution densities in training. And this is really how many targets we have distributed over the Earth. In this work, we consider a few different distributions. So when I talk about a uniform distribution, I'm just referring to points uniformly distributed all across the Earth. Likewise, the city distribution distributes points at the locations of cities on Earth's surface. We train all of our agents for 5 million steps using the RL-lib implementation of asynchronous PPO, and this corresponds to roughly 11 to 14 years of mission time, or 10 to 15 hours of compute time on 32 CPUs. As an aside, and you can read the paper for more details about this, the variable intervals do make learning more difficult. So as a result, we have to train for finite episodes and then include the time of completion through the episode to be able to learn the value function. This doesn't impact the final policy, but it does allow us to learn a pseudo infinite horizon policy in a finite environment. So to implement this simulation, we've been developing a tool called BSK-RL. So the RL portion of that comes from the standard Gymnasium API used for reinforcement learning. BSK comes from Basilisk, which is a fast and flexible spacecraft simulation framework that's developed by the AVS lab. This uses C++ as a backend, Python as a front end, so it's both very fast, but also very easy to use. And put them together, we have our BSK-RL repository, which allows us to easily create customizable environments for satellite reinforcement learning research. And so we inherit the best of both Basilisk and Gymnasium. We get our modularity from Basilisk and the high fidelity from Basilisk. And then, of course, through Gymnasium, we get our compatibility through all of our major reinforcement learning libraries, whether it's stable baselines, RL-lib, via those standard Gym and Petting Zoo APIs. This package is completely open source, as you can see with the link up on the screen. And the current focus is Earth observing flight mode tasking, but of course we can extend this to other areas of interest. So next, now that we have our whole problem formulated, we're talking about how we're training our agents. How good do our agents do? So to evaluate our agent, we're going to look at the quality compared to a mixed integer programming-based solution. So we varied the state space look ahead M, so how many targets we get in the state observation. Also varied as N, the number of targets that the satellite is picking between for its actions. And finally, the different target distributions that I've mentioned, we tried training on each of those. So first of all, the look ahead, so that M value has very little impact on performance. We see that the three agents trained on the uniform requests perform pretty similarly, and the three agents that were trained on the city requests also performed pretty similarly. The really nice part here is that we see that our agents that are trained on the uniform environment are able to be deployed in the uniform environment and get between 80 and 100% of the reward of the mixed integer programming solution. Keeping in mind, of course, that this is 10 milliseconds of evaluation per step, as opposed to hundreds or thousands of seconds of evaluation for the mixed integer program to find the solution. When we try and deploy in the city's distribution of targets, it is a little more challenging. We see that none of the training methods do particularly good. As we get to high densities, it becomes a very challenging problem, and we're maybe getting between 60 and 80% of the total reward that the mixed integer program can. And unfortunately, trying different training distributions or different look aheads really all produce about the same results. The nice thing, though, is that we see that the uniform training generalizes nicely to the city deployment, and that's because locally, anywhere within that city's environment is roughly uniform. So it does have experience within a density of that type from training over a range of densities in the uniform training case. So what did this policy actually learn to do? We see that it learned a long horizon policy. If we look at the mixed integer programming solutions with those dashed lines versus the PPO solutions with the solid lines, the performance across the length of the simulation, the number of orbits there, doesn't really change for the RL-based solution. And they're all pretty close to the 15 orbits of the longer horizon case for the mixed integer program. And this makes sense. We want to learn the long-term best performance. We don't want greediness in short horizons. It also learns a very different policy than what the mixed integer program does. It favors taking fewer higher valued images. And we surmise this because that's ultimately an easier policy to learn. It's a lot easier to say these images or these requests are soon, they're worth a lot, let's try and get them. It also explains why using a longer look ahead in the action and state spaces didn't help, because really the policy has learned that most of the time it's best just to look at those next few targets and find one of the highest value targets that it thinks it can reach before its opportunity window closes. The biggest challenge here is the number of missed targets. This is how many of the images or how many of the requests that the satellite attempts to get versus how many it actually fulfills before the opportunity window closes. In the uniform results, we get relatively good performance between 90 and 95% of the attempted images it successfully takes. However, when we look at the city requests, we see highly depressed performance there. And this has to do with the fact that the cities can be very tightly clustered in certain places. So just predicting whether it's possible to do some of the very short slews between those tightly clustered cities can be difficult. And as a result, it's easy to attribute most of the decrease in reward between the mixed integer program solution and the reinforcement learning-based solution just to those missed targets. So that's really a area of future work. Finally, we want to introduce some constraints into this problem by creating a power-limited problem variation. So for the power-constrained problem, we want to introduce a highly nonlinear power model from our spacecraft simulation. So this is going to be including things like the bus power draw, the reaction wheel power draws, which are a nonlinear function of reaction wheel speeds, the instrument power draw, and then finally power generation from the solar panels, which are body fixed and anti-parallel to the instrument's pointing direction. We add a charge action to the Markov decision process. So this is just an action for the satellite to slew to point its solar panels at the sun for 60 seconds. And then if it wants to, of course, it can do the action over and over to charge for longer than 60 seconds. And the agent fails if the battery goes to zero. And this is a difficult thing to model in anything less than a complete simulation, because the attitude and the rates of the spacecraft really all highly influence this power system. To account for this power limited case, we need to modify the training process. We include the eclipse times in the observation so that the satellite can learn to associate power generation with whether it's an eclipse or not, and whether it should try and charge during those times. We also include information about the upcoming reward density in the observation. And this is just the sum of rewards in each of the next 5-minute intervals. This allows the satellite to really anticipate, are there segments with lower reward coming up? And if so, if I'm able to, I should wait to charge until then. To further help with this, we use a new training request distribution, which I refer to as a Swiss cheese model. And it's the same as the uniform targets, but just with random regions of those targets removed. And that allows us to add periods without targets into the training domain to really encourage learning that sort of behavior of you should charge when there aren't targets around. Finally, we use a shield to guarantee safety when we deploy these agents. And all the shield is it's a deterministic response to certain states if the action that the agent selected is unsafe. In this case, that really takes the form of forcing the agent to charge if the battery level is below some minimum threshold to be able to stay alive and make it through eclipse. So the power limited performance, we want to compare these various policies to a power-free baseline. In the cases that we look at are unshielded training with both unshielded and shielded deployment and varying our failure penalty. We look at shielded training and deployment, and we look at just taking our power-free policy and adding a shield on top of that. For uniform requests, we see that the unshielded policies all tend to fail over higher request densities as the time moves on through the simulation. And this is because the satellite really never learns that, or really keeps wanting to get reward because there's always reward available. And as a result, it never decides to stop and charge. However, we can see by just adding a shield on top of that, so that solid dark gray line in the upper left plot, we can not lose very much performance while then keeping our satellite alive all of the time. And we see that it's a nice balance between the amount of time that charging happens because the agent wants to charge versus the amount of time that charging happens because the shield is overriding the agent's decisions. In the city request, we see even better performance because here there are these gaps over the ocean where there's no reward available. And as such, the agent can learn to charge there and then just perform as normal the rest of the time. In both cases, we see that zero penalty, unshielded training with shielded deployment performs best. So that's what we'll continue to look at after this. One interesting learned behavior that we see from this policy is an expected one that we were hoping to see, which is that the agent does in fact learn to charge during gaps in reward. So because of that training on the Swiss cheese target distribution and by including the upcoming target density in the observation, which we kind of see in that green bars at the bottom of the plot, we see the yellow highlighted regions where the agent decides to charge pretty much always correspond to regions where there isn't much or any reward available. Another even more interesting emergent behavior that we see from these policies is that it learns to increase the amount of passive power generation during imaging actions. So if we compare the power generated during imaging actions due to the attitude of the solar panels between the power-free policy, so not thinking about power at all, versus the power-limited policy, which did need to learn how to manage its battery in addition to generating reward, we see that the power-limited case ends up generating a lot more power during imaging hours than the power-free case. So what's going on here is that our satellite's actually picking to image targets that happen to also point the solar panels at the sun, and as a result, increase the amount of power that the satellite has and decreases the amount of time that the satellite needs to spend on dedicated charging, thus overall maintaining higher reward and spending less time on charging actions. This is a really remarkable result that I think is unlike anything that a human planner or another planning algorithm would be able to easily or obviously come up with. So I'll leave you here with the same animation we saw earlier. We can see the charging occurring over the oceans as well as all of the reward collection. And thank you for listening to this presentation, and be sure to check out the paper if you want more details.